So we discussed that a three-phase inverter consists of 6 switches that are turned on in a particular sequence to produce an output which is 120 degree apart, and yet it is a three-phase balanced output. So we discussed that one scheme is to use a 6-step inverter that was actually an improvised version of a square wave scheme. In this, every switch conducts for 180 degrees, and therefore output between this A and N turns out to be a 6-step output, and that is why this is known as the 6-step inverter. We should notice here that this the naming here S1, S3, S5 and the S4, S6, S2, this nomenclature is based on the time instant at which we turn on these particular switches. Thereafter, we saw that the problem with this 6-step inverter is the same as that of a square wave inverter, because the fundamental frequency or the switching frequency of this switch S1 till this switch S6, it is all equal to the base frequency, which is equal to 60 Hz. Therefore, the harmonics appear at quite close to the fundamental component. So if this is the fundamental component, we saw that the harmonics appear to be at around 6k plus minus 1. So again, we have harmonics available. So therefore we said that in the next class we will discuss about how to implement the PWM schemes for the same type of an inverter. So if we use for instance, let me draw here the three-phase inverter again. So we have this DC available here. This is switch number 1. This is the arm number 1, and then we have this is leg or arm number 2, and this is the third phase. So we are tapping out the load from this particular point. So this is A, and this is B, and this is C, and we have discussed that this A, B and C can be connected to either a Y connected load or a delta connected load. So this one S3, S1, S3, S5, this was S4, S6, and this is S2. So if we use a sinusoidal PWM scheme to turn on these 6 switches, then we can actually incorporate all the advantages that we have studied for a single phase PWM scheme. And those advantages are that we push the frequencies further from the fundamental frequency, and therefore the filtering becomes very easy. However, as we have seen in the single phase PWM scheme, instead of having a single sinusoidal reference waveform for each arm, for example, if this is A, if this is for A phase, this is for B phase, and this is for C phase. So for each arm or leg of the three-phase inverter, we require a separate carrier waveform. Notice that to have a balanced output, because if, for example, we want to generate an output of 60 Hz, then for a balanced output with a balanced operation, we require to have this VA reference, which is this one. VA reference should be equal to VB reference and should be equal to VC reference. And by equality sign, I mean that their amplitude should be the same. It is just for the amplitude. As far as for the phase is concerned, then V of A, if it is equal to at 0 phase, then V of B should be at 120, and V of C should be equal to at minus of 120 or 240. So that all the 3 waveforms are actually 120 degree apart from each other. Next, what we need to do is we need to generate a carrier waveform that is again a high frequency signal, a triangular waveform, through which we compare these 3 waveforms, VA reference, VB reference and VC reference, and we develop a scheme that is used to supply the gate signals to this S1 and S4, S3 and S6 and S5 and S2. If I move further, the switching control is as follows. So if this V of A is greater than this V triangle, then we are turning on this switch S1. So see here, this is VA reference. So this VA reference for the time when it is greater than the triangular waveform, then we have S1 on. So this means that during this particular time instant, this VA reference is actually greater than this V triangle, so we are turning on the switch S1. And similarly, if we have this triangular waveform greater than this VA reference, then we should turn on the switch S4. Also, you should note here that like all the inverter schemes that we have studied so far, we cannot turn on this switch S1 and S4 simultaneously. So we need to have a scheme that develops only 3 gating signals, that is for S1, S2 and S3, and thereafter we can use a NOT gate operation to supply for the switch S4, a NOT gate operation to supply for the switch S5, and for this switch S6. So you can see here that if we somehow generate these 3 gating signals S1, S2 and S3, then we can actually use a simple NOT gate operation to ensure that both the switches of a similar leg do not turn on simultaneously. Because if it happens, there is no way we can reduce the shoot through this DC source, and this VDC will be shorted if we turn on this switch S3, S6 or any of the 2 switches simultaneously. So what we have developed here with the scheme here is that we have S1 on when VA is greater than V triangle. You can also see if we reverse this thing, VA is less than V triangle, then we reach to this particular state, which is the S4. And you should also see that S1 and S4 belongs to the same arm of this H bridge. The second thing is S2 is on when VC is greater than this V triangle, and for this S2, if this VC is less than the V triangle, we turn on the switch S5, which is the high side switch of the third arm or the arm C. Similarly, we have this S3 is on when VB is greater than the V triangle, and S6 is on when VB is less than the V triangle. It should also be noticed that we can minimize the harmonics in the output spectrum if we choose our carrier frequency f of C, which is a triangular wave frequency, if we choose it to be an odd triple multiple of the sine wave, that is 3, 9, 15. So for instance, if we have f of sine wave, which is shown here, which is this one, which is the reference waveform, this sine wave, if we have a frequency equal to 60 Hertz, if we want to generate a frequency of 60 Hertz, then the wisest thing is to use a frequency of a triangular waveform which either has 3, 9, 15 and so on and so forth. So if we use it 9, then this should be at least 540 Hertz. That is if we want to minimize the harmonics in this particular content. Also, you should see here that we have this type of a waveform available. So this is VA0, this is VB0, VAB and VAN. So let us understand what is this VA0. So for 3-phase inverter, this is, let us suppose this is connected to some load. This B phase is connected to this load, and these loads are all balanced. That is, there is no difference in the values of these loads, and we call it, this is the neutral point N. This is VA, this is VB, and this is VC. So 1, 3, 5, 4, 6, 2. These are the switches. Now what is this VA0? VA0 means that we need to develop a scheme where we have a sinusoidal source. For instance, this is a sinusoidal source that is compared with a triangular waveform. So this is the high frequency triangular waveform, and this is the comparator here. So the output here is passed through a limiter block that limits the value between 0 and 1, and thereafter it is ready for this switch S1. Now this switch S1 is having a NOT gate operation for the switch S4. Now if you manage to see what is the voltage V here, then this V is equal to VA0. This is the VA0. This is the VA0. And also for VB0, we need to have another sinusoidal operation here. So we can say that this is VB, this is V of A reference, this is VB of reference, and we need to have another thing. So because this particular triangular waveform or this V carrier, this is same for all the three switches. So again we can use a limiter block here, and this gives me for S2, and a NOT operation is actually performed for this S2, and we have above we have S5. So this is S5. So you can see that this particular point, this is equal to VB0, VB0, and the voltage between this particular point V of A, after that we have applied this particular thing, this will become equal to VA of N. For the phase-to-phase voltage, the obvious choice we have here is to measure between this VA and this VB. Similarly, in the similar fashion we did for a 6-step inverter. So VAB here is equal to V of A minus this V of B. So this V of A0, you can see here that we have the widest pulses available at the mid of the waveform, and that is because of the sinusoidal PWM operation. That is because of the sinusoidal PWM operation, because the amplitude of the sine wave becomes higher when it reaches the 90-degree period. So you can see here between this period, if this is V of A, between this whole time we have this V of A higher than the triangular waveform. So a pulse with the maximum width appears at this particular center, and that is what we can see in this particular area. So this is that particular waveform that is appearing in the highlighted section. Similarly, we have this VA of B available, and that in turn equal to the similar results as that of a unipolar PWM scheme. So you can see here that this VA of N is actually providing us some information about the current as well. So if I can somehow, if I can zoom it somehow, let me show you. Okay, so this is a very interesting sort of result. So you can see here that for this period, when we have this V of N positive, then I of A has a rising slope, and that rising slope is because of the inductive load we have, and thereafter this V of N equal to 0, and therefore this slope is equal to 0, because V of L is equal to L di over dt. So if we do not have a voltage here, then we do not have a current. So the current slope is equal to 0. That is equal to 0. It means it's a straight line. Then again during this period the current rises, and for this very small period the current actually has a very small downslope. Thereafter it again has the 0 value, and so on and so forth. The current shows the graph that is quite similar to that we discussed in the DC to DC converters. So let us move ahead. So let us move ahead to the next slide. So we have the Fourier coefficient that are present in this 3-phase inverter. They are actually of the they are calculated using the same methods that we have seen for the single phase PWM inverter. The thing here is that the normalized values have a different table. This is taken from Daniel W. Hart, the textbook. You can see here that the table is different than that we use for a single phase inverter. So don't confuse these two tables. We cannot have the same harmonic spectrum table for a single phase and a 3-phase inverter. Rather, these two systems, 3-phase or a single phase system, they have a different table for the normalized amplitudes in case of a PWM voltage. So therefore, whenever we want to see what is the harmonic spectrum in a PWM three phase inverter, we have to use this thing. And I have earlier described you that these tables can be generating using modern software techniques like MATLAB or MathCAD. You can go there and you can program the output to get these type of things. Another thing here is that this is a normalized amplitude. This means that it do not shows you the phase, the phase difference, or what we call the phase inversion. You may have these some of the components with a negative sign, but we are actually getting the normalized amplitude with an absolute value. So we are not concerned about that they are actually phase shifted. So in the next part of this lecture, we shall shortly see how to simulate a PWM three phase inverter, and we will understand that how we relate the frequency components of that are present due to the harmonics with a three phase inverter system. So let us do the simulation. So before we move on for the simulation part, there is just a small mistake. This is M of F. This is M of F plus minus 2. This one. This is not equal to 2. This is plus minus 2. Similarly, this is equal to 2 MF plus minus 1. Now this table is a very brief table that explains only till the frequency 2 MFF plus minus 1. However, if you move on to the one of the reference books, which is by Ned Mohan, in its table number 8.2, it gives us a lot of other values, including 2 MFF plus minus 5, and thereafter we have 3 MFF plus minus 2, 3 MFF plus minus 4, and then 4 MFF plus minus 1, and so on and so forth. So however, by using this table, we can actually simulate the given problem. So let's go to the simulation part. Now I have developed this three-phase inverter, as you can see here. So we have this switch S1, S3, S5, and similarly we have 3 switches connected on the low side. For the gate driver circuit, we have developed this scheme here. So you can see we have this sinusoidal source available here, with an amplitude equals to 0.7. Notice that we have for the carrier waveform, the peak to peak voltage is equal to 2 volt, which means that if I may draw it here, this triangular waveform shall have a peak value on the positive side equal to 1 and the negative side equal to 1. And with this sine wave equals to 0.7, this database says that this M of A is equal to 0.7. So for the simulation process, this M of A is equal to 0.7, and that is set by putting the value of peak to peak voltage equal to 2 for this triangular waveform, and 0.7 for a sinusoidal waveform. So we are expected to have an output frequency equal to 60 Hertz. Notice that for VA of for this VA reference, we do not have any phase angle and associated phase shift. However, here we have included for with minus 120 degree. Again, because the operation should be a balance, therefore the other two waveforms are also set at amplitude equal to 0.7. An interesting thing here is that because we discussed that this M of F should be a multiple of 3, so we have because this value is equal to 60, so this M of F, which is equal to which is set at 9, therefore this V triangle is equal to 540 Hertz. It is set at 540 Hertz. So that we have now 3 comparators instead of having 1 comparator in as we saw for the single phase PWM inverters. This is actually a limiter that limits the values between 0 and 1, so that we get a proper gating signal for all the 3 legs of this particular 3-phase inverter. Notice that this VA of A, we have used this label block to avoid unnecessary routing here. So this VA of A is connected with this switch S1, and through a NOT gate it is connected to switch number S4. And similarly, the same thing have been done for this VB and VC. In addition to that, we have used a load that consists of a 10 ohm resistance in series with an inductance of 20 millihenry, and that is true for all the 3 loads. Load should be balanced, otherwise there will be harmonics in the output. Now we have set all the three values. We have set this amplitude equal to 100 volts. So we are actually transforming this 100 volt DC supply into a three phase output. Notice that to measure the A of n, we have used this voltage sensor. Also, we have a voltage sensor connected between these two legs, which gives us a value equal to VA of B. So we are getting VA of B here. Also, we have connected an ammeter to probe the current through this A load, and we call it this I of A. So before we begin, let us have the simulation control. Let us check this thing. This is equal to zero point 0.1. Total time is 0.1. So let me simulate this one. So now that we have simulated this thing, first of all, let us see what kind of carrier waveform and the reference waveform we have. So we have this VA reference, VB reference, VC reference, and this V carrier. Let us plot them all together here. So you can see here. Let me change the color here of this V carrier, because this is difficult to see. So now you can see here that we have, let me show it for a brief few cycles. So this is VA of reference, and we have this is VC of reference, and this is VB of reference, and this is the carrier waveform. So you can see here that the peak amplitudes of these sinusoidal waveform is set at 0.8, and for the carrier waveform it is equal to 1. So after that, let us see what kind of output we are getting at this particular point, that is the gating signal for switch S1. So for that, the probe is VA is in A0. So let me draw that here. So you can see here, this is the VA0. Also, we need to plot VB0, and this is the VB0. And notice here that these were the same kind of results we have seen here. So this is VA0 and this is VB0. As far as this VAB is concerned, if I plot this VAB, then this VAB should look like this particular waveform, and this is exactly the same as we expected as we expected here. The next thing we need to see is this VA of n. So VA of n is this kind of a voltage with the current I of A. So let us plot the two entities. So this is I of A, and this is VA of A of naught. So if I plot it here, so you can see that this this is not VA0, this should be VA of n. Okay, so now you can see here that this current is difficult to visualize. So let me get rid of this VA0 screen and this VB0 screen. So after that, we have deleted this thing. So let us also delete this VB0. So now you can see it is still not visible. So one way is that I actually provide it some shift by multiplying it with some value. Let us say it is equal to 20. So if I multiply it by 20, then we have quite a good waveform here. But just let to may have more clarity, let us change the color here to red, and a little bit of line thickness. So that is the current that we witness in this particular section. So let us assume this particular section to see if we are getting the same result as we analyzed in the theory. So you can see here that whenever we have a voltage applied, then we have a current which actually increases, and thereafter it decreases, because these values are not exactly the same. Therefore, you can see here at this particular point, this slope is approximately 0 when we do not have any voltage available, that is VAN is equal to 0. In addition to that, we are more interested in seeing the harmonic spectrum here. So let me delete this particular graph here and see what kind of harmonic spectrum we expect for this VAB. So for that, let us take this FFT here. So you can see a lot of harmonic content is visible in this FFT. So, but we need to restrict it to some sane value. So let us say we restrict it to the 19th or 21st of the harmonics. So that means we need to restrict this x-axis to 1260 hertz. So if I place it equal to 1260 hertz, we get this type of a result here. So now you can see that we need to elaborate this with respect to this particular table here. Now because this m of a is set to be equal to 0.7, therefore the fundamental component should have a value equal to 0.606. So if I may say, this should be the value we should get for the fundamental component. And because this VDC is equal to 100 volts, so therefore we expect to have 60 volt for the fundamental component. So if I move here, this is the fundamental component at 60 hertz frequency, and you can see that this VAB has 60.6 volt available, which is exactly the same as that given in this table. The next thing is that the next frequency component appears at M of F plus 1 is 2. This means that the next frequency component at M of F plus 1 is 2 should appear at, because this m of f is equal to 9, so the next frequency element should be at f7, and thereafter the next element should be at f11. Now this f7 is actually a multiple of the fundamental frequency, so this is equal to 420 hertz, and this f11 should be equal to 16 to 11, that is equal to 660 hertz, and both should have an amplitude equals to 0.015 of the DC amplitude. So if I see here, if I take it all along here, this is the frequency at 420 hertz, which is the seventh component, and it is having 1.5 e to the plus 1, which is equal to 15 volt. So we are getting exactly what is elaborated in the table 8.8. So also we should see that the next harmonic should appear at the 11th harmonic, which is at 660 hertz. So at this 660 hertz, you can see here it is again at 1.51 e to the plus 1, which is equal to 15.1. Thereafter, if we see this table 8.8, the next harmonic content appears at around 2 m of f plus 1 is 1. So 2 m of f plus 1 is 1 means that we have 2 into 9 plus 1 is 1, and that is equal to, it should appear at 17th and the 19th harmonic. So the 17th harmonic means that we should see a frequency of at 1020 hertz, and also we should see at 1140 hertz. So at 1140 hertz we should see amplitudes which are greater than the amplitudes at f7 and f11, that is equal to 0.30, sorry, this is 0.307. So if we see here, we should get 30 volt for 120 hertz and 30 volt for 1140 hertz. So if I go here and if I make it all the way to this particular point, this is at 1020 hertz, and this 1020 hertz is actually the 17th harmonic. The amplitude VAB is equal to 30.6 volt, and thereafter we should see at F19, which is a 19th harmonic, it should appear at around 1140 hertz, and that is also equal to 30.528. Notice that as we move along with this particular for harmonic spectrum, the next harmonic should appear at 2 m of f plus minus 5. So if this 2 m of f plus minus 5 means, because this m of f is said to be equal to 9, so notice that if we extend this particular harmonic spectrum to some other frequencies, we may see some other hidden components that are not explained in this particular table. For instance, as I have mentioned that this 2 m of f plus minus 5 exist in the output frequency spectrum. So if for this particular example m of f is equal to 9, this means 2 into 9 plus 5 should exist, and 2 into 9 minus 5 should also exist. That means that 18 minus 5, we have this 13th harmonic should exist here, and also sorry, this is 23rd, and this is the 13th harmonic. So the 13th harmonic is f of 13 is equal to 60 cross 13, that is equal to 780 hertz. Also we have f of 23, that is equal to 60 cross 23, and that is equal to 1380 hertz. That is equal to 1380 hertz. Notice that using this table we cannot distinguish, we cannot determine what is the amplitude of this F13 and F23. However, if we move here, you can see here that if I zoom in this particular area, if I zoom this particular area, you can see that we have this 660 hertz, which is the 11th harmonic, and thereafter, as we have mentioned here, that the 13 harmonics also exist. So this 13 harmonic exists at 780 hertz. So you can see here, if I move here at this 780 hertz, we do have a very small value, which is 0.78 volt. However, it exists. Also, if I can zoom it for this particular area, so you can see here that for this particular value, which is the 13 harmonic, which is the 1380 hertz, we should also have the same value here. So for this value at 1380 hertz, at this 1380 hertz, let us move the cursor to this 1380 hertz. This is 120. So we have this 1380 hertz, we have 0.64 volt here. So again, we do have some voltages that appear across this 2 MFF plus minus 5. Also, the next harmonic should appear at 3 MFF plus minus 2, and 3 MFF means, because this MFF is equal to 9, so 9 cross 3 is equal to 27, 27 plus minus 2, so we should see a 25th harmonic as well as a 29th harmonic. So the 25th harmonic should appear at 1500 hertz. So at this 1500 hertz, if I move here, so you can see we have a substantial peak here that consists of 17.5 volt. So that is how, by using the simulation, we can extend the numerical results we get, because of course these are also based on some mathematical tool, for example the MathCAD. However, if it is not available and you further want to see the shape of the harmonic content, you can always use the simulation to verify these things. So in the last, we need to just remind you, let us summarize the inverters that we have studied. So for an inverter system, we have studied the full and a half bridge converter that can be used to synthesize an AC output. Also, we studied the quasi square wave inverter, and we studied how we can simulate those inverters. And then we simulated the square wave 6-step inverter, and today finally we simulated this inverter, which is actually a pulse width modulated 3-phase inverter. That is how you can actually simulate these things to validate your results. I encourage you to solve the end numericals and simulate them to further strengthen your knowledge. Thank you very much.